Okay, so we're back here, 12.1. I just finished giving you a more than necessary analysis of QB touchdowns to salaries. And now we're going to talk about determining significance of linear regression. So I did it here in these. And so there is a table of critical Pearson correlation coefficients that we call R sub alpha, critical coefficients. And it's based on alpha equals 0.05 and 0.01. This is in the ebook. It's I want to say Appendix I, something like that. But you can also Google this. The Pearson correlation coefficient is a standard thing, just like z-scores and t-scores. So if you Google it to find that chart, you're not going to get different ones. And so we say that R is statistically significant. That's an important difference here. If R is greater than or equal to R sub alpha. And so with this comes a test for significance, because we want to make sure that we're sure of that significance. And so these, as I mentioned in the beginning of the last video, these are hypothesis tests. So a significant linear relationship in a two-tailed test, we have our null hypothesis H naught is that rho equals 0, and the alternative is then that rho is not 0. Because remember, significant linear relationship or not significant linear relationship, the default is that we have no significant linear relationship, and the alternative is that we have, there is significant linear relationship. And then we do break it into negative and positive linear relationships to test the tails. So this is all based on the fact that R is always between these values, -1 and 1. So if we're going to test the left tail, the left side, those are only going to be negatives, negative slopes, negative linear relationships. And our alternative hypothesis and null hypotheses, the null here is that rho is greater than or equal to 0. And the alternative is that rho is less than 0. And so the idea being, we're checking this against the sample statistic R, and so we assume by default that there's no negative linear relationship. Notice that this says nothing about whether there's a positive linear relationship or not, because we're testing the left side. So again, if you think about it in terms of how we thought about z-scores, you have to be so far to the left or so far negative to actually be certain that there is a strong negative linear relationship, if that is the case, being the alternative option. And then same thing for significant positive linear relationship. This is a right tail test. We're looking at just the positives here. So we assume by default, or I shouldn't say assume, but by default the null hypothesis is that rho is less than or equal to 0. And the alternative then is that rho is greater than 0. So these are our three tests, our left and right tail tests and our two tail tests. Our test statistic is T. This is not the same T as in t-score. It is, but it's calculated a different way. So this is R over the square root of 1 minus R squared all over n minus 2, where R is the sample correlation, n is the number of pairs, and the degrees of freedom we use is n minus 2. And so we calculate it this way because this is a relationship significance, testing that regression that you would have, like we calculated up here, to see if it's statistically significant. So if we're going to do a test like this, we have to have some rejection regions. So that's what we'll talk about next here. So for the two-tailed test, we reject our null hypothesis when the absolute value of our t-score is greater than or equal to t sub alpha over 2. For a left-tailed test, Since it's only one tail, we're not going to be looking at t sub alpha over 2. We'll be rejecting our null hypothesis if t itself is less than or equal to negative t sub alpha. And for the right tail test, again, we're not going to look at alpha over 2 because it's just the one tail. We reject our null hypothesis if t is greater than or equal to t sub alpha. So this is telling us it's at the tails, it's either greater than or equal to t sub alpha over 2 or less than or equal to negative t sub alpha over 2. This is specifically far to the left tail, less than or equal to negative t over alpha over t sub alpha. And this is the right tail if we're significantly larger than t sub alpha, our critical t score. So let's take a look at a full example doing this. So use a hypothesis test to determine if the linear relationship between number of parking tickets a student gets and their GPA during the same semester is statistically significant at the level of significance alpha equals 0.05. So one thing that I like to do with these is first actually look at the scatter plot, so we don't talk about scatter plots just for nothing. So if you wanted to enter this data, the first thing we would do is go to our lists and put our data into list 1 and list 2. So we're going to make this one list 1 and this list 2. So I've gone ahead and entered that into my calculator. Number of tickets in list 1 and GPA in list 2. So we do have to do, you can't see that, the glare is too much. We do have to do something on the calculator to make sure we can see the scatter plot. So what we need to do is we need to hit second and then the y equals button. So that's second, and then this button right here is y equals. And this is our stat plots. This is our stat plots window, and so what we want to do is hit enter and make sure that plot 1 is on. Now, if you're in other classes that are using the calculator, you want to make sure that you turn this off when you're not working in it because it will always plot your list 1 and list 2. So that can be a little weird and mess up another class and vice versa. You want to make sure that we've cleared our equation editor, which we'll talk about in a second. So make sure that's on. Yours is probably off right now, and so you want to make sure that it's on, and then you scroll down that the on is highlighted. So we're going to quit. The next thing you want to do is make sure that your equation editor is clear. So hit y equals and make sure there's nothing in any of these. Clear those out if you have something. And then we hit graph. And it doesn't matter if you don't see anything. What I like to do is do zoom fit. So hit the zoom button. And then I think it's 9 is zoom fit. Zoom stat, that's what we wanted. Zoom stat. So this will automatically zoom into our statistics. So we can see what our data looks like in a scatter plot. So what we see here is a general trend down. As the parking tickets go up, the GPA drops, generally. And so going into this problem, before we start doing any hypothesis testing, I want to be thinking this is probably a weak linear relationship. And it's good to check your stat plot, your scatter plot, because it allows you to think about what am I actually aiming for here. If there's no linear relationship in the scatter plot, then that will inform your results of your hypothesis test. So now we can run our hypothesis test. So we are just looking to see if there is if it is statistically significant. So this is a two-tail test. So our rho for our null is that its rho is 0. Our alternative is that rho is not 0. Because it didn't ask us is it a significant negative or significant positive, it just said see if there is if that relationship is statistically significant. Our alpha is 0.05. And so our degrees of freedom is our number of data points there are 13? No, there's 14. 1, 2, 3, 4. 15? Oh, it's m minus 2 now, right? That's what I said. Yeah, so 15 minus 2 is 13. Excuse me. So our alpha over 2, we're going to need it, is 0.025 because we're doing a two-tail test. And so looking at our t sub alpha over 2 value, this is 2.16. And remember, to get that critical t-score, you're just doing the inverse t. And so our test statistic t is using our linear regression. So that's why another reason why you want to put it in to check your stat plot to see what kind of relationship you're looking at. Go to calculate and down to linear regression. My R value here is negative 5, negative 0.586619. I like doing 6 decibels as a hangover from error calculation from confidence intervals. So that's why I'm doing 6 decibels. So T then is negative 0.5886888619 over the square root of 1 minus negative 0.586619 quantity squared all over 13. And this comes out to be negative 2.612. So it's okay that it's negative because remember we're doing a two-tailed test. So we can be in either tail. That's why our rejection region, as we have up here, is absolute value of t. The test we're looking at, is this greater than or equal to t sub alpha over 2? So the absolute value is 2.612. And compared to 2.16, this is greater than that. And so that tells us that we should reject our null hypothesis. And so what does that mean? Well, that means that there is sufficient evidence to determine that there is a statistically significant linear relationship between parking tickets and GPA. Draw a line because the problem is over. And so we've determined there is a statistically significant relationship. Now, the question I want to pose to you, to have you think about here, is do you think this is always true for this situation? Is there always a statistically significant relationship between linear relationship between parking tickets and GPA? So take a minute, think about it. And I'll tell you now, the answer is no, this is not always true. And that's because there's a lot of factors that go into this. So especially factors that regard the sample that was used. So think about when you normally would take classes, if we were on campus right now. Do you normally take your classes in the morning, in the afternoon, in the evening? Well, parking tickets are inordinately distributed between those 3 times. Generally, people in the evenings do not get that as many parking tickets as, say, someone in a 8:30 a.m. class. Because a lot more people are taking classes at 8:30 a.m., and so the spots fill up a lot faster, which means that you could end up parking illegally or parking without getting a parking pass because your class is about to start and you have an exam and you're just trying to get there. And you said, well, maybe today they won't notice. So this is not going to always be true. And in fact, if we look at our R value at negative 0.5 here, it's right on the cusp. So it's larger. We would describe this as a strong linear relationship, but we know that the data in the scatter plot doesn't look like it. So we would want to collect more data. Obviously, we only had 15 values here. And I've said this before. The more data you have, the better statistics you can actually calculate. So let's turn the page here. How we interpret statistical significance. So now we've seen an example of how we actually test for significance using a hypothesis test, and we did the two-tailed version. So there are 4 types of relationships that we can see. So the first type is that X influences Y. And so X is affecting Y here. We'll just circle it. The second is that Y could be affecting X. So here, Y influences X. This would be the case where we chose a response variable that actually should have been the explanatory variable. But it's possible, right? Because we're thinking X and Y are just 2 data sets. We also have the case where X, Y, and a third variable Z all influence some combination. So X influences Y, but Z influences X and Z influences Y. So this would be X influences Y and Z influences X and Y. And we can also have, coming over here, an X, Y, and Z case where X and Y aren't influenced at all by each other and Z does the entire thing. So this would be Z influences X and Y. Now, each of these can still have a linear relationship, a weak or strong linear relationship between X and Y. And you can probably guess that this one undoubtedly should be a weak linear relationship, but sometimes that's going to appear strong in your data. So what we have to kind of suss this out is the coefficient of determination. So this is denoted as R squared, and this is the coefficient of determination. This tells us the proportion of variation in Y, our response variable, that can be associated to the variation in X, the explanatory variable. So in other words, when you see a big change in Y, R squared tells you the percentage of that change that our explanatory variable is responsible for. So the more significant a linear relationship we have, the stronger the linear relationship we have from X to Y, the higher your R squared is going to be. Think back to our football examples here that we talked about. If we square this, it's going to be close to 1. If we square this, it's not going to be close to 1. So that means that a lot more of the change in QB rating is associated with touchdowns, whereas change in salary is not as associated with touchdowns. At least the percentage change in salary can't always be as associated with touchdowns. So I know that this video is also long, but this is our last example of the section, so I'm not going to stop and start another one. So this would be a somewhat long section. I apologize, but here we go. So if the number of rooms in a house is tested for significance with the house's prices is run, I worded that very poorly. So we are testing significance of house prices. It's run, and we find that our significance, or our correlation coefficient R, is 0.65. How much variation in house prices can be associated with the number of rooms? So this is just to explain what this R squared does. So our R squared value then is 0.4225, right? So you just square 0.65. So what this tells us is that 42.25% of the variation or the change in house prices can be attributed to change or variation. Let's say variation, that makes more sense in this sentence. In the number of rooms in the house. And this makes sense. You know, even if you're just a renter, the higher the number of bedrooms there are and bathrooms total, the higher the price of the house is, the higher the rent of the apartment, the higher the rent of the condo, whatever it is, goes up. And so what this study would have found is that 42.25% of the increase or decrease in price is associated with a change in the number of rooms. And so what that tells us as an analyst is that this is a huge deciding factor on what dictates price. And in fact, I'm sure you've had a situation where you've looked at a house to buy or apartment to rent, and the rent's really high, and you get there, it's in a bad neighborhood, or it's in a bad building that has a lot of work, there's problems, paint's peeling something, there's roaches, whatever it is, and you think, well, how can they charge so much? Well, it's because the number of rooms is playing such an important role in what that price gets set as. And so this is something that gets looked at whenever someone starts linking two sets of data. And especially when you have things that can be quantified, like house prices especially are a really notorious thing in real estate to overanalyze why prices go up, why prices go down, and you know, room numbers is just one of those things. The other major contributing factor for house prices is square footage. So you'll see a much higher square footage space is going to have typically a higher price. Now, if it doesn't, maybe it's 1,600 square feet, but there's only there's only one bathroom. And so you start seeing these things kind of balance each other out. So that's how you interpret that coefficient of determination. So even though we have 4 types of relationships, each one can have linear relationship. We use the coefficient of determination, our R squared, to tell us what's causing the most fluctuation. So if you're looking at 3 things, this is the best situation here. If you're looking at a response variable and an explanatory variable that has a third variable that's affecting it, that change in y, you look at the coefficient determination from y and z and from y and x. You'd set up 2 different linear relationships, 2 different linear regressions, and you'd see which one has a higher R squared, and that would tell you what's the main controlling factor. Okay, so I know that this is a little long, 2 long videos, and I apologize for that, but this is a heavy-duty section, but it flows right out of Chapter 10 because it's a hypothesis test at its core.